So, thank you very much for the nice intro. My name is Kirill Hrustalev. I work for PTS, OSI Noble Gas Techniques, and I will introduce this panel, which is on radionuclide innovations and how they can be useful for CTBTO. The panel members represent different countries, and they all are experienced radionuclide scientists. I will briefly introduce them all, starting with Anders Ringbom. He has a PhD in nuclear physics and is a research director at the Swedish Defense Research Agency. He has more than 25 years experience developing equipment and analysis methods for CTBT verifications, and especially he is the father of sauna, let's put it this way. Sophia Brander, she works at the German Federal Office for Radiation Protection, where she's a radio xenon scientist. Kira Rezina is working at Cypressdorf Laboratories in the ATL03, one of the IMS laboratories, and she's doing her PhD on novel high-sensitivity radioactive xenon detection system. Pa02 Krisangakura is a nuclear chemist at the Office of Atoms for Peace in Thailand. She has experience in environmental radiation monitoring and supporting the installation of IMS station RN65. And she's also a trainee in the third cycle of OSI surrogate inspector training. Vladimir Popov is a nuclear engineer with long experience in the development of radioactive xenon sampling and measurement systems, and he's currently working in engineering consulting. And the last member of our panel unfortunately couldn't make it today, but she provided her comments, and I will be talking head or voice for her. Her name is Pune Tayebi, and she's a research scientist in the Nuclear Science and Technology Research Institute in Tehran, Iran. So the session objective is to assess, discuss topics how developments in radionuclide cutting-edge technologies and novel materials can be applied for CTBT, understand whether the RN monitoring systems have reached the desired level of maturity and what can be done in order for them to reach this if they're not. Use remotely controlled platforms in the field of radionuclide detection. This is especially for OSI. The use of radionuclide data fusion tools, and the next steps in the development of radionuclide detection technologies. So I pass the mic to Anders, who will be serving as moderator for this discussion. Thank you.
Thank you, Kirill. And it's a great honor to be here on this stage and with all these distinguished panel members. I just want to start by just putting this a little bit into context, what we are going to discuss. As most of you know, we have the IMS radionuclide network, 80 particular stations and 40 radio xenon stations, and it's a unique machine that is actually the world's only global measurement network for radioactivity, and it has a few things that are unique more than that. For instance, the systems we are using they have high time resolution compared to most national systems that maybe have several days of sampling time, for instance, and so on. We have also a system with a lot of automatic particulate and radio xenon machines. And that's also quite unique as well, but also a challenge sometimes. And then thirdly, we have noble gas stations, as I said before, which is also pretty unique, but they are also starting to spread outside IMS as well. So the task we have is to, as you all know, detect, locate, and characterize releases that we see. And we have to distinguish the background from the signal, and that is a challenge we have. I mean, we are talking about a multidimensional space with many isotopes and also location, and we try to find the best signal, dig that out from the background. Then we also have the radionuclide labs as well that can be used to measure filters and noble gas samples as well, remeasure them. as well. And then, of course, we have the on-site inspection, which adds other technologies as well, or measurement techniques like soil and water samples and subsoil sampling of noble gases as well, and airborne measurements too. So that's just to set the context a little bit, what we're trying to discuss here today, with respect to innovation with these systems. So, we have divided this a little bit into themes, and the first theme we have is measurement instrumentation. Questions like, what novel technologies in sample collection and sensor design could revolutionize the sensitivity of radionuclide measurements, for instance? And let's start with Kira. Maybe you can tell us a little bit what you are doing at your work and start to discuss this question. Thank you.
Thank you. So thank you for having me. So I'm working in the Austrian lab right now, and I'm building a beta-gamma coincidence measurement system for noble gas. It's based on a well-type HPG detector and a plastic scintillator cell as the better part. The idea is that it has a 4p geometry, and so it should help the coincidence should help to distinguish between the metastable isotopes, xenon isotopes. I think we saw already, like for the past couple of years, that there is a clear trend to moving away from single gamma spectrometry to beta-gamma coincidence measurements for just to distinguish the metastable ones. I find it quite interesting because there's like a few options there right now. For example, like the PIPS box, and which is like right now for SPALEX and G, or like I already saw some papers having the same idea as I have with the plastic scintillator. I think this is something that will continue to go on, and there will be also a lot of improvement in that direction. I'm also very interested in seeing how different detectors will be mixed and matched. For example, like the CZT with the PIP box, and like a combination trying to reduce the measurement time, so we have like faster analysis, can faster react to things like that. And I heard yesterday also like a talk about coincidence measurement for particulates, so gamma-gamma measurements, and I think this is also something that is a very interesting topic to explore and see how it will go on with that. So if someone wants to add something, go for it.
Sophia?
Yeah, sure. So you talked about radioxenon measurements, I guess. Another thing that comes to my mind is the xenon array idea. That's the idea of having like several smaller measurement systems instead of having one large IMS station, and has a lot of advantages in if you have some maintenance or something, you still have the other array members that will be able to measure. We are much better with source localization if we have several detectors instead of just one. So this is something that Anders has worked a lot on. There's so many different things that you can work on or that are being worked on. Also, sampling times can be shortened. That's also really helpful to have smaller SRS fields, what we call them, like when you measure something, then you need to do some atmospheric transport modeling to find out where the air came from, basically. And if you have a shorter sampling time, that area is going to be smaller. So that's very helpful also to identify possible sources. And that's always the quest that we're on, right?
I can give you another aspect of from the developing country. So I'm Ch1 again from Thailand. So I'm work for the radiation monitoring. So I think they know these two ladies. She's like focused on the detector, the sensor, which is it's for us. I mean, for the developing country, it's kind of very costly to invest. So we kind of focus more on the novel of the technology of the collecting sample, which is we kind of like the electrostatic aerosol sampling, which is you can collect the sample that are very low concentration, and you get a good sample for detection. As for Thailand, I don't know that many of you been there, but it's very humid. So sometimes sensor that's how good the sensor is, sometimes it doesn't work there. So we kind of focus on another angle that would be enhanced of our detection. Thank you.
I also would like to discuss.
Microphone.
I think it's closer.
I think also important to talk about minimization of the.
Держи вот.
I think it's very important to talk about minimization of the Xenon system. Now, CTBT has OSI equipment and IMS equipment. It's big and sophisticated machine, very reliable for the current moment. But in some cases, we have, from my point of view, it's important to have a small, robust unit which can be used like a redundant system for IMS stations. For example, after the third North Korea nuclear explosions, we have a problem with our RX Xenon system at the Surisk. And within few days, we brought in our suitcase a sampling and sample purification system together with the detectors. The weight of system at fall was about 90 kilograms, and then can bring it in ordinary flights. And within few weeks, we successfully operate this system. 10 years ago, we developed a special sample preparation unit for OSI system. It was a really small machine which can put it in one suitcase. I think it can be used for like redundant system, for example, for the sauna cube. If something happened, but we all know in the field, all can be happened, and not always positive events. You have possibility to produce a sample with small power consumption unit, which have robust design and give you chance to not lost all information about the Xenon. And additionally, I have a presentation today, a poster, about big sample technology. It's a completely new approach for Xenon measurement, because now IMS and OSI equipment can produce not more than a few cc of pure Xenon for measurement. And this system and now is very close to this theoretical limit for the MDC, for MDC. For this purpose, we developed a technology when we can get not few C, but 100 cc of pure Xenon, use the production of air separation plant and oxygen plant. There are a lot of installations around the globe, and for this purpose, we also use very small units for sample preparation, which can easily to bring to different part of the world, and you can measure Xenon with real recordable MDC about 10⁻⁵ power becquerel for Xenon isotopes. And in this point, very important to have robust small size transported unit which can be installed everywhere in the world. And I think it's significant improve treaty verification regime and can be used for different purposes.
Thank you. I would just like to, in addition to the previous panel comments, I would like to read a statement from Pune on the emerging technologies such as nanostructured scintillators and nanophotonics, which offer higher light yields and faster response times and enable detection of very small amounts of radionuclides. So this will improve the detectability, and she also recommended what Kira said before, combination of a CZT with these new scintillators, which can improve the sensitivity of these systems, so a hybrid system.
Okay, thank you. Oh, yeah, sure.
I think it's quite interesting to see that different parts of the world will also have different necessities. So it's a question about the cost, it's a question about the weather, how robust it has to be. It's something different to have an IMS station and something different to have a lab, which has a different system and has different requirements. So I think it will be important that we have like different options to use, especially like some countries does not have the money or the opportunity to invest a lot of money in it. So we have to have something that is cost effective, not doesn't need a lot of maintenance. So we also have to consider that, because we have to have a network that works everywhere and not just in specific parts and forget other parts.
Now that you bring up the labs, we also discussed this yesterday already a bit, because obviously we prepared for this panel, that we think that the labs are a bit underused at the moment. Like right now, we do have labs, like all of the labs can do particulate reanalysis of samples, and some labs can do xenon reanalysis. Particulate filters are reanalyzed regularly if they're like level 5, but radioxenon samples are not reanalyzed on a regular basis, only for spike samples. But there could be so many other things done at the labs. For example, for the particulates, it's really important also for atmospheric transport modeling to understand the sizes of the particulates. So this could be something that could be investigated further by the labs. I mean, there's all this field of radiochemistry that can be done on the filters to understand many nuclides way better and to really determine the ratios properly. And I think we saw this in the ruthenium case pretty well. Remind me of the year.
2017, right?
Yeah, okay, thank you.
Okay, thank you. So, yes, I just wanted to, we talked about small scintillators a little bit here. And so, I mean, I can see a small trend here for early warning detectors sitting on the filter itself as well. And just a comment, I think that could be also useful. You don't want a big plume from, for instance, like we saw in the Fukushima case, that could also cause like harm for the operators and so on. So I think that could also be a useful development.
Yeah, yes, I think it's, we saw a talk earlier yesterday, I think it was on the improved electrostatic sampling, and they are already designing this warning detector as a integral part of the sampling system. So it's a good improvement. Okay, so this, I guess, I have a thought here about, brings us a little bit to a question how, I mean, we have a few ways to develop these systems. Larger volumes, shorter processing times, and better detectors and so on. And for instance, in the xenon case, we have now the next generation xenon systems that we have increased the volume, and the sampling time is shortened like 6 or 8 hours and so on. And people already ask me, okay, what about the next generation? What's going to happen? I mean, the Sonar 4, 5, so that raises the question: how good do you really want? Do you need to measure? I think bring this up now, maybe. Yeah.
So what do you think about this? I mean, how is it really necessary to measure one atom in 10 cubic meters of air, or what do you think about that?
I don't know, I don't really against that, but it's more like it's complicated for me, because when you do the installation, the new thing, you need to rethink the infrastructure that required there. And later, it's a maintenance that you need to do. And the knowledge that people can capture, I mean, locally kind of thing. So we don't really want to jump into something that's so fancy.
Yeah, but for radio xenon, for example, we've been discussing a lot about different ratios. And there's this idea that we can always classify an event by looking at the ratios of the different isotopes. So for that, like at the moment, we are not so good at measuring the isotopes that are not xenon 133. So we detect xenon 133 a lot, but xenon 131M, 133M, and then 135, they have lower occurrences, so we don't detect them so often. And if we really want to use the ratio method, it would be really helpful to have lower detection limits on the metastables and xenon 135.
From my point of view, the duration of the measurement sampling and volume of the sample depends from the type. And the modern, the new noble gas system has to be adjustable for this. For example, if you know that there was some suspicious about possible test, you have to try to find metastables, all the confirm that this event was, and you can maybe increase sampling up to the few days, and have possibility to measure huge sample that find some useful information. I mean, metastables isotopes, especially 133M. It's not easy, but it's preferable that it was. And another things I think is very important. It's a QC measurement. And quality control measurement, it's not ordinary measurement every day. I mean the spike measurement for all stations around the globe, that we, society can trust this the result which we got and demonstrate. It means we have to regularly provide special tests for all xenon equipment and check laboratory as well. And it's possible only when we can produce, especially Sibisdorf, for xenon isotopes, and may provide valuable and result.
I mean, when we talk about stuff like that, I always think about the background, because this is one of the most important things. Because the background is dynamic, so we have to measure it. We have to see, like, catch everything that there is. If there is a release something, we have to catch it. So we want to get as good as we can, so we don't miss something, and we have to distinguish between the things. I think this is a theme or a topic we cannot ignore when we talk about, like, how good we want to be, because we want to be as good as we can, because our circumstances, especially like the background, is so dynamic. So we have to strive to be like better, always better.
Yes, and we also should remember that we have different backgrounds in different parts of the globe, so that's also important.
Definitely.
Yeah.
If I may, so I would like to return to Pa02's comment about reliability, and it's very important, because we have to trust, as Vladimir said, we have to trust the sensors and the data delivered. And over the course of the history of development, I remember a lot of detector systems which were developed, for example, pulse shape discrimination, which worked very well in a lab, but they never ended up to be deployed in the field because of their complexity or reliability. So this is a very important aspect. Yeah.
All right, I think we could move on to the next theme we selected, and that we call it autonomous systems and drones, actually. And Pa01, you have been working with OSI and are doing that right now. So what are your thoughts about the most promising applications of autonomous systems and drones in the field of radionuclide detection, particularly in hard-to-reach or high-risk areas, for instance, always in the OSI context.
Okay, thank you, and yes, I think I'm the only one from that joined the OSI. Okay. Well, I think at the moment, the OSI section, they don't have the drone or any autonomous system, right? But I think it's become nowadays very popular tools that been used in many fields. And well, that's also for the radiation detection as well. For the OSI context, we work, I mean the inspector, they work in the restriction condition, like a limited time frame and also limited of the number of the inspector. So with the, I mean as a trainee, I wish that like we could have some, we could have some. For both the airborne and the ground-based. Okay, it can extend our work without putting the inspector at risk. When you do the OSI, you don't know where you're gonna end up with in the area, which is you have no idea. You actually got some information, but still, if you the team leader, you don't want to send the people out there without knowing anything. So with the drone equipped with the gamma detectors, you can quickly mapping the area for the radiation mapping. And with that, you get information. And nowadays, it's not just, I mean, the commercial one, nowadays, it's not just the radiation detector that they put it on the drone. You can have the radar, you can have the camera, GPS, and everything. So the information out there that you got, it's not just the number. You can see the landscape of the area, which is important for the OSI. It make you can like well strategic your mission plan, and then later if you see the land and you get some idea, and you can do it quickly for sampling plan, where you wanna get the sample and what kind of sample that you wanna have, so that the ground-based robot can come to play a role, that you can go in and get the sample that you want. Now we have backpack, so you use the manpower. If you see the surface rupture, you can just walk around the area. But you cannot cross the swamp or the rupture part. But with the drone or with the robot, you can get the information over there as well, which is kind of extend your hand. That's what I would say. And last but not least, I think because we have the limit of the inspector, so the point of the consistent and reliable data, the measurement data, is also important for the OSI perspective. So with the robot, with the autonomous system, so you can reduce the variable of the different operator. So it's more convincing, because sometimes we have the limited RN expert. Sometimes they cannot go out, and we have to rely on the seismologist expert, and sometimes they don't really know how to operate, and maybe struggling with the equipment and so on. And The autonomous system, you can now pre-program the route and everything. So which is, you're going to get consistency of your data. Thank you, that's for me.
Is any other one has a comment on this? Vladimir?
I have shared some small thought about during the Ch1 measurement is very sophisticated task and very important apply creative approach for data analysis. For example, especially it can be useful for on-site inspection. What I mean, if you not see radioactive xenon in one sample, you can use produce from the few sample one spectra and maybe try to catch track, because especially for OSI, we have limited volume of the sample. You can use different approaches for the spectrometry. It's and realize some idea on the fly. It can be useful to make a track of the xenon.
Thanks.
I'm thinking like more of a very simple approach. You talked about like cameras and stuff like that. So in the middle of like climate change, we have catastrophes. There's a good chance IMS stations will get damaged. So there's a good chance just to like take a drone, send it up, have a check, does it work, what happened, is it safe for people to go up there? So it's just also for simple maintenance. It's also, I think, quite an easy way to do it and probably like more safe.
Okay, thanks. So we got a question here in the chat, and it says like this: currently, all the radionuclide monitors in the IMS sit on the Earth's surface, but radionuclide in the atmosphere are transported in a three-dimensional space. Do you think we will reach a point in the future where we can measure the vertical variation of radionuclides on a routine basis? Okay.
Yeah,
Yeah.
so I think the answer to that is putting samplers on commercial airplanes, right? I mean, airplanes are flying around all the time, so...
But how to interpret this data if you're collecting?
Yeah,
over long
ATM will have to move forward a bit, I think, to interpret that. But it would really do like high altitude sampling.
I think that one way was also to, I mean, it's important for the atmospheric transport modelers to have actually data also in that direction. And we have been thinking about, you could also maybe use a tower, like the cube, the sonar cubes. You can have one on the surface, and you can have maybe an inlet far up, maybe 100 meters or something. And already that would give you more information on what's going on, actually, I think. So that could also be something to think about. All right, so we already talked a little bit about miniaturization. So maybe we should go on to analysis, because I think that sometimes, or very often actually, when you talk about these things, it's all about the machines, the measurement systems, the equipment. And we are physicists, chemists, and we want to measure as good as possible, and we focus everything on how we can improve our measurement system as the best we can and be more sensitive. We discussed this already. But sometimes you forget the analysis part of it. And if you look actually when you plan a network of some kind, the cost of work, developing software and everything is actually quite a lot of that is in the manpower doing the analysis or developing things and software and so on. So that's easily forgotten. So I think that we should also talk about this. And so, Kira, what do you think? How might the new advancements in AI and machine learning be applied to radionuclide measurements? And how could these advancements impact CPT monitoring, you think?
So I'm thinking there's like no way around it. It's such a big topic, so we have to do it at some point. I think, in my opinion, what will happen is it will especially machine learning and AI, will be used, for example, for simple analysis, just to check like standard measurements, standard samples, to see if they're like vary from what we expect, vary from what from the background we're expecting, and like flag it. So what it does is, of course, it gives the person who does the analysis like more time. We can separate it a little bit more, always having like a person behind the AI who always checks it, just to ensure that it's like we don't miss something. I think it will also go in a way, because especially like coincidence measurements are quite complex. It will be definitely help there, at least some help to analyze this. And I also think it will also be a part in ETM models and like figuring out samples, and if some samples are coming from the same plume, for example, like trying to connect them. I think this will also be a field where especially AI and machine learning will be a part of.
Anyone else want to? I think the thing you mentioned here, that the plume association thing is really important, and it's something that is one of the big challenges we have in radionuclide community, actually. And I see we're talking about radionuclide events. Which samples are connected together if you have a plume? And that is a challenge, and do this to find an automatic way to do that. It's not easy, but it's, as you say, really, really important. And we have seen some examples of how we can use machine learning to do that also. And I think that's one way to go. Yeah.
It's like, I can add that for the machine learning, that what we did in our station, but it's not really the CTBT station. But for the machine learning, we collect the data and we kind of make them recognize the pattern of the spectrum, and that's lead to kind of seasonal pattern of radionuclide that reading, because we have the tropical season and the summer. So sometimes we have a lot of radon watchout, and so we kind of teach them to have the pattern recognition. And it's not all the same for all region across Thailand, but we kind of, okay, this is from this region, this is from this region. And that kind of screen out noise for us. I mean, yeah, like an innocent alarm kind of thing that could be useful for the AI or machine learning.
Yeah, I saw a talk today on this where they also classified the particulate spectra and saw like which spectra came from the same station or not. And in the beginning I thought, like, why would you even do that? But then I also thought, for example, of the NPE 2024, where some fake detonation events were used, and it's really important to know that your spectra are actually like from the station that it's been claimed. So that's really helpful.
If you have a lot of the data history, so you can predict that's where it's come from, or it's really from there.
About machine learning, some sort. I think it's very useful and more simple way use this approach for the quality control of the spectrum. What I mean to check the calibration, resolution, and energy calibrations. But for the working spectra, I think now this main operator is required.
I mean, I remember a discussion like a year ago, which was like someone who's not that fond of AI. The question was kind of like losing the ability to do analysis. The more we use AI, the more we use machine learning, the more like the humans lose the ability to do the analysis themselves. But I think it's just like, for me, it's just a step to improve in different like fields or different like subjects or different like very specific points. and using the AI like for more regular tasks, quality control, stuff like that are like normal in a normal day what we use. So we can focus on more important, more specific stuff, more as out of the norm.
I think also AI can be used as a data fusion tool for, especially for example in the OSI context where we collect information from many different techniques, and at some point we have to integrate all of this into one single report, and AI is really great at finding correlations and helping associate events and provide additional information about the overall picture.
I can just mention one more. I'm talking about the cubes again, sorry. But we collect with the radio xenon arrays a lot of data. I mean, in Sweden we measure now 40 samples a day or something like that. Well, not a day, but we have for the 4 isotopes. We get a lot. So the data is vast, and it's not easy for the human eye to find all the connections, to find the anomalies. And I think to try to find those patterns in the data is actually the way to go for us there. So we have been talking about ATM now a little bit, but we can focus a little bit more on that question. So what are your thoughts about the use of ATM as a data fusion tool, and what other technologies may be useful for data fusion of the RN measurements?
I mean, I think ATM is one of the most important things we have. We measure things, we get like data, we get a concentration, we get an activity. We have a number. It doesn't tell us anything else. So we have to use ATM to understand like what is the source, where does it come from, associated with other samples, finding out the plume, finding out. It's like such an important tool for us, combining like with seismic information, combining with all information we get. I cannot imagine doing it without it, especially like backwards ATM, like going back and finding the source of what we measure, but always also forwards ATM, trying to figure out if an event happens, we know event happens, which stations will be probably hit with it, and also preparing for that. And also, it's also, I think, helpful for example, labs, so they know there might come a sample, there will be a particulate which is important, or xenon sample, which they can prepare for getting it. So I think like both things are very important, and it's like a very important part of our work.
Yeah, I definitely agree.
Okay, so, but there are also challenges. We have been working now for many years with the uncertainties of the atmospheric transport, and I guess that is something that we have seen quite an improvement and a lot of work being done, but still ways to go. It's so complicated. So I think that's also a challenge in the future. But we see great work with the ensembles, for instance, so trying to quantify this, but it's a challenge. But I think that's when we get this more in a standard way, as a maybe some kind of product or something, I think that would improve things also a lot for a non-ATM person, because also that's the thing, we are different communities here, and we have to be able to talk to each other, the ATM people and the people that are doing the analysis of the radionuclide data and so on, and try to meet. That's also, I think, a challenge.
I think coming back to the first topic about the measurement systems and ATM, we could see, I think during this week, in a lot of talks where people were analyzing data collected from sauna cube arrays, for example, and just by having an array and with different baselines, it reduces the ATM uncertainty a lot by having these multiple detections or non-detections. So it's a good fusion between technology and interpretation of the data.
I think going back to, again, background, it's also quite important because we have a dynamic background, so we always have to use ATM just to check it, because at some point we're getting non-typical samples, non-typical analysis information, and we have to kind of figure out what happened. Is this something that will occur more often? And things like that. So I think it's just something that is so deep in a lot of work yeah, that's kind of like so important.
We have a question about, well, it's more about in general. So currently we have many IMS stations, but the question is, what prevents the development and deployment of scalable, low-cost radionuclide monitoring solutions in developing economies? And is it truly a matter of funding or political will, technical standardization, and knowledge sharing in deploying such solutions?
So that would be like beyond IMS stations.
Well, it doesn't specify in the question, but I guess, yeah, it could be a contributing national facility, or we have some examples already, for example, with small arrays in Lithuania or in other countries, if this could be considered as an extension of and useful for CTBT.
Yeah, definitely. I think we just need to figure out how to share the data in a way that's acceptable to the member states also. And I think, yeah, for that we need to really educate people about what we're doing. And you also mentioned funding, so the systems are pretty expensive, and then that's the one thing you need to maintain, to do maintenance on them. That's pretty expensive as well. And then you need the experts, like really, yeah, to gather the knowledge. So I think, yeah, we have a couple of countries where there's a lot of expertise, and other countries are, I hope, learning and catching up.
Before we leave the analysis part, I think we still are there, maybe. I would like to just mention one more thing I think is very important. That is to understand the source and to have good modeling of the expected releases, both for the background sources and for nuclear explosions. And because we are looking at isotopic ratios, and we use them to compare in different plots with scenarios. And these scenarios are simulations. They are also have uncertainties in them as well. And I think that's also something that could be more discussed, actually, how to improve this. And I've seen great work on this, but I think that also the uncertainties of nuclear data, for instance, as well. Because we compare our data with models, and that's how we get our hypothesis. So I think that's also something that we need to work more on, actually. Yeah.
We have a question, so maybe just I will just read it. So it's a question from Pune, and maybe with this we can follow into the next theme. The knowledge is boundless, but when it comes to increasing the sensitivity of nuclear detectors, how do we determine the appropriate limit? At what point do we decide that further enhancements is no longer necessary? And I think this is going to radionuclide innovation very much.
I think we touched upon it a little bit already. So,
I mean, I can make like a short answer. At least for me, it might be a little bit naive, but I think there is like no real limit, because it's kind of a balance thing. We try to measure the smallest amount to understand it. The other side is trying to hide it as much as they can. Therefore, it's kind of like going hand in hand. We trying to strive to be better and catch everything, and the other side is trying to hide it as much as they can. So I'm kind of thinking there won't be a real limit, because there's always the possibility we miss something, and this is like the worst thing that can happen in our system.
I can add up from Kira. When is enough? When is enough? I think, well, it's kind of depend on what you're looking at. If you reach the goal that you're looking for, it's good. I think that's enough. And for the detection, I mean, if the signal to noise is too low and you pick up so many noises or signal, it's going to be mislead for your reliable data. And also, another thing for us is like if the cost of the investment is outweigh the benefit, it doesn't do good for at least for me.
I think it's never enough. Because if we would like to determine the nature of the event, we have to measure as more as possible. And this is the reason why we start to implement big sample technology when we have a huge sample, about 1,000 cc of 1,000 cubic meters for each sample. It's give to us a real chance to measure in each sample 4 isotopes and better study background or determine some events. It's not belong to the CTBTO stations, but it's give to us chance to more deeper study xenon background around the globe.
I mean, I understand your point. I think we have to distinguish between like innovation and people or like countries having the ability to invest in it and like striving to get better, especially like thinking 50 years ahead. We don't know what will happen. We don't know what improvements will come, but I think there will be a lot. And it depends, like countries that can do that and have like the money to do that is one thing. A different thing is making it, of course, available for other countries who may not have like the money to do it or the knowledge or the simple opportunity or the manpower to do it. So improving it in one case and making it available to the others is kind of like an important thing. But the basic idea of just improving a system or improving like labs, which can do like another measurement and be maybe more sensitive, is something that I think there is no limit to that. Definitely there is a limit in like IMS stations kind of cost and maintenance and stuff like that, and just human and manpower. How many people are there to do the job?
All right, thanks. So let's then go to another question, and this is, we are working here in a political context. We have a treaty with a very detailed, also technical part on the verification system. And at the same time, we have the world around us with academia and innovation, which is accelerating. We have seen talks today about this. And how, and the process to move these new technologies into CTBT verification could be sometimes slow because of the political context as well. But how could a CTBT-centered innovation pipeline connecting scientists across, for instance, borders, accelerate the deployment of next generation radionuclide detection technologies, do you think? It's kind of a broad question, but Sophia?
Yeah, so I think you already mentioned it in the question, and I agree with that. It's like the innovation is not going to come from the governments or the countries, but either from academia or maybe also from the civil society. And in order to reach academia, I think this is already a nice setting where we invite people from universities to come to the CTBTO community, but I think we as scientists should also get better at going to different conferences and going to academia and maybe start some interactions with universities. I don't know, for example, we have a physics and disarmament professorship in Germany, so we try to interact with them and maybe try to get some students that want to do a master's thesis on CTBTO topics. So to really like spread our themes into these other spaces, because I think people are working on things, but sometimes they don't really understand what like the real world life problems are that we have. And it's also good to have this free space where you can just think very broadly. And that's what academia is very often. But sometimes it's also good to have like a connection between us who are like working on data analysis every day and the people that can sort of explore what they want. And as I already said, S&T is one of these places, but we should also try to go to their places more. That's my opinion.
Any other thoughts on this?
I think the workshop and doing exercise together is also one of the that we can get involved with the people from academic and also from the people who are in charge. Sometimes the station is the government. So the exercise and get people more involved in what we are doing. It's also, you make people involved, so it's kind of more practical in a way. And for the novel technology to be implemented by the CTBTO, I think it's going to be a lot of work that we're going to put it into place, right? I think you kind of need the member state consensus to have that, right? So I think that if you make more the member state aware and involve a lot of that in the aspect that we study, like a new technology, and they can see the benefit, so that could make also the benefit from that.
Yeah, and I think a way of doing that is also if countries set up their own national networks, for example, and then they can really build this case, for example, for the SonarQube network, or Germany also has had a network for a very long time, and then, it's easier to convince people with something that you have already done than with something that you're planning on doing. So that's also a way forward that we have.
We kind of trying, not just in the country, but in the region, because we're quite small and it's not really high technology. So we kind of get together with now we try to have the network like a European one. So that also another way that we kind of working on.
I think I can also give you an example of outreach, because outreach is important here too. I mean, to increase the like you said already, increase the awareness of CTBT. And we tried to do that in Sweden, but we actually set up a course together with Uppsala University. It's called "How to Detect a Nuclear Explosion." I mean, completely CTBT verification related course. It started as a PhD course, but now maybe it will be a master's course actually. That could be one way also to attract more students, because it's important to do this, and it's also actually interesting science, I think.
I think that's very interesting, because I think just like the public itself is not quite aware of the CTBTO and what we do and the work we do, and I think if there will be more awareness and the importance of our work, there might be a little bit more pressure to the politics, and it might move things faster and forward.
Okay. I think we're done. Should we complete this?
We can also take some questions from the audience if you would like to have any our opinions on any of these topics. Please come ahead.
Apparently we covered everything.
Yes. Also, it's almost 5 p.m., so people are tired.
We should call it a day.
Yes. Okay, so thank you very much for attending our panel discussion. I hope it was useful and interesting for you as well as for us. And of course, we know each other quite for a long time. But it was, when we were preparing for this panel, it gave us fresh thoughts, and interaction is always very important for moving science ahead. So I think this forum, like SNT and the other workshops and conferences where we participate, is very important on moving innovation into the practical field of CTBT. Thank you very much, and have a good day and the rest of the conference.